I'll pass you over into the capable hands of Arun Magesh.
Hello, and thank you so much for coming, like, for example, after lunch, and also the last talk. Yeah, so I will try to make it not as boring as possible. So to give a little bit about myself, I work as a principal security consultant at OneKey. It's not the hardware wallet company, so it's the automated firmware analysis company. So my primary expertise are mostly in the chip security, and I also do a bit of IoT reverse engineering, embedded pen testing. And I also recently got a bit into compliance and everything. Boring part, but somebody has to do the work. So let's get into the main part, the fault injection. This is a very generic term. For example, if you talk from a software world, fault injection could be anything. For example, if you do a fuzzing, that is also a fault injection. Or if you're using a buffer overflow or XSS, so they're also considered fault injection. But today, what we are focusing is mostly on the hardware side. Because your software runs on the hardware. And for example, even if your software is super secure, what if some attacker can actually inject a fault on the hardware, and then maybe they can bypass some security? What are different things that you can use it to inject fault on hardware? Or for example, your computer needs power. So what if an attacker can manipulate the power that goes to your, let's say, a microcontroller or any device, for example, and then change some code path? You can use anything, for example, voltage. You can also use laser. You can also use electromagnetic field, even temperature, or even, for example, sometimes you throw a device and magically something happens, and then your security is bypassed. Some rare cases, even gamma radiation from outer space can also inject fault in your hardware. For example, there was an election in the US, so where one of those gamma radiation flipped a bit, and the voting went really high. So this is a simple example. In a typical case, a device will have a safe voltage range. For example, in this case, it's around 3 to 5.5. But what happens if you're, for example, playing with the voltage level so that you're dropping your voltage to a very lower point? So we're not talking about dropping for 5 minutes. So here, the dropping the voltage means for a few nanoseconds. For example, there'll be a bunch of instructions, and then you glitch at a specific point where your CPU doesn't have enough power to execute it. At that point, your CPU will either be corrupted, or it will just skip the whole instruction, for example. And you can also go for EMFI, that's your electromagnetic fault injection. In voltage, you have access to the voltage line, you can glitch it. So if you know the high school physics, so if you keep a magnet next to a wire, so there will be some current that passes to the wire. It's something similar. So here we try to inject those current in the silicon itself. So if you take silicons, there's a bunch of transistors, and then you have small metal layers that connects each transistor to form your CPU or whatever. And then you can use this to also inject your faults. And there's also, you can use laser as well. You can decap the chip, so you only expose the raw silicon. And then you can also inject, let's say, a very small spot-size laser to, let's say, select a specific transistor, shine a laser in it, and then you can just flip a bit in it. From a normal user, this doesn't make sense because it's just a glitch. You reset your machine, and then everything works fine. But for a security perspective, this could really be a serious threat. For example, this is just a simple check signature function. This is mostly used in secure boot. For example, your mobile phone has secure boot. So if somebody tampers with your system partition, your device will not boot. So in the inside, it basically does, let's say, for example, SHA-256, and then compares the expected hash value with the calculated hash value. And if it's correct, it's going to return true, and then your boot chain starts. Or else, let's say, it's going to be false. How would an attacker can actually do it? So if you look at it from just a coding perspective, you can most likely delete the whole if condition. If you delete it, then by default, your return true will work. Or if you were to change the other part, you can probably rename the true to false and false to true. So these things, let's say you have source code, you can modify it, and then you can bypass it. What if you don't have source code? What if, for example, you want to attack it from a hardware perspective? That's where fault injection comes into picture. Fault injection so far has been a research topic for almost 15, 20 years. But the last 5 years, it has been really coming into the market. For example, your Nintendo Switch jailbreak, So they are using fault injection, or for example, the AMD SMM bypass, your AMD processor secure boot, that has been compromised by fault injection as well. So for this one, let's talk a little bit about my setup. So in this case, I am using a small microcontroller. That's STM32F103. That's an ARM Cortex M3. And then I have my own glitching device based on another microcontroller. So this is basically the template which I'm going to run. So in my case, I will send a command, A, and then there'll be a specific GPIO. That's basically a pin that basically triggers high and then goes low. And then all my code will basically go between that one. So that is for me to actually know, OK, this is where my process starts, this is where my process ends. And this is a bit complicated to understand. So ideally, I'm just powering the board, the blue pill, that's my target. And then I have my PC that runs some Python script. And then I have my teensy. So that one basically takes the signal from PB5. And then it has a MOSFET. That's basically the one that injects the glitch. So for example, in this case, it's going to 3.3 voltage lane. For a few nanoseconds, it's going to short the 3.3 to the ground so that your CPU doesn't get enough voltage for a specific period of time. From the analog world, it will look something like this. So your yellow one is your trigger. So once it goes up, that's where your main operation starts. And then your green or blue is your glitch. That's your power. So for example, in this case, I'm injecting 2 glitches. So for example, that's around 1.2 microsecond. It goes slow. So during that period, your CPU will not enough energy, or it could just be anything. Yeah. So some of the parameters you should consider is, for example, you have a huge window. Let's say the trigger pulse. Let's say if it's around 10 microseconds. So that is where operation is performed. So which means that's sort of time correlated. So here there are 2 things which you need to understand. One is the glitch delay. So at what point of the trigger you are actually injecting the glitch. In this case, it's almost around 2.5 microseconds from the trigger. And then the glitch width is basically how thick your glitch width is. For example, if you give, let's say, 10 nanosecond glitch, it's too short that your CPU will not even care. Or if you're giving, let's say, 1 second, which means it's too large that your CPU will not even work. So the next step is to actually find these very specific parameters which your specific CPU or your chip is vulnerable to. It's the same. So how do we do that? So we have something called as characterization. This is where we use it to find those parameters. And this will be unique for each setup. It will be unique for each configuration or each chip as well. It's a simple loop. So if we are just counting 50 twice, the output will be 2500, and it is between the trigger of going high and low. And I basically run it for several thousand times. And then we have a plot with respect to the glitch delay from what point from the trigger to the end, and also the glitch width. If you see, like, if your glitch width is less than 200 nanosecond, it's going to be green. Green signifies that nothing happened. So your chip just works fine. It didn't affect anything. But if you go more than 200 nanosecond, you can see it's all purple, which means the glitch got so powerful that your CPU stopped responding. So, but if you look in the middle, you can see the red. So red is where the sweet spot where you can actually make your chip run and also corrupt the instruction. So in this case, in the middle, instead of getting 2500, I would probably get like 2100, or even, let's say, 4500. So we are basically glitching these instructions to change the code flow, for example. Yeah, now we can, since we know these values, now we can only focus on those values. Here, the objective is to get more glitches for an attempt. In this case, I can. Since it's a loop, you can see the glitch happens on all the ranges because it's a sequential loop. So even if you hit anywhere, you can skip a couple of instructions. And you can zoom in to it more, and then you can rerun the test, and then you can get more glitches. So what are the different things that could happen? One is instruction skipping. For example, if there is a secure, for example, string compare, what if I skip the whole string compare? Let's say I glitch in such a way, I'm not executing anything, I'm skipping the branch to memcopy or branch to strcpy, and then go to next instruction. That's also possible. Next one is instruction corruption. That's way more dangerous compared to skipping. You can actually flip bits. For example, if you have a branch to function number 1, you can actually glitch that branch to a opcode, which could relate to branch to a different function. So which means you can probably even have your PC go to somewhere else, or your LR goes to different values. And your cross-domain glitches are, so sometime when you glitch, for example, the voltage or the chip, it's not just the CPU you are glitching, you are basically glitching every single component of it. For example, if you have your hardware crypto core that's running inside, you don't necessarily need to glitch the CPU. You just need to glitch the external. For example, if the RAM, you can also glitch the RAM, and you can also do cross glitches as well. So this is a very simple example. We have toString. It could be a hash. It could be a password. It could be anything. In this case, if the hash value is correct, it's going to be set to true or else false. If that is the case, it prints me pass or fail. Based on that, I will run a loop. So here, there's no protection. It's just as it is. It's how you would implement it. But if you think from a programmatic perspective, it looks perfect. Unless, for example, some hash collision, then you can bypass it. But technically, this seems like a pretty secure code. But if I glitch it, I can probably, you can see I can glitch it. If you look somewhere around 1250, you can see there are some reds, which means I could bypass it to get a pass value. So now here, at least in fault injection, you don't look at the C code because C is very abstracted if you're injecting, let's say, single bit glitches. So in this case, we have the same code. We have the string compare, and then the count is checked with if the return value is 0, and then you get pass or fail. But if you look at in the assembly part, there are 3 sections that are happening. So maybe my mouse works? Not. Yeah, so first is where all the data is being loaded. For example, you are loading the 2 string values inside a register, and then that being moved to R0 and R1 for a string compare. And then the return value goes to R0, and then goes to R3. Again, we are comparing if it is 0 or not. And then we have branch not equal to. That sets the value to count 0. Can my mouse go there? Yeah. Oh. Yeah. So we have branch not equal to. If it is not 0, then it goes to this loop, sets the count value to 0. And if it's not the case, it sets to 1, and then you print. So the scope is only under this one, because we are pulling the pin high here, pulling the pin low here, so scope is only here. So what are the different models for this attack? Is, let's say, we have the move instruction. So if you compare the 2 registers, R2 and R3, so what if we glitch the instruction so that instead of moving R0 to R2, we can convert to R0 to R3. And the difference is just 1 bit. You just need to glitch 1 single bit, so the instruction is converted into move R0 to R3. And similarly, for the next instruction, you flip it to R3 to R2, and then you basically have the 2 variables have the same value. So then your string compare will obviously say it's correct. And that's one. And this is the branch. Earlier we talked about in the code, can we, for example, skip the whole string compare operation? So in this case, it will not really work. But if you look at the code carefully, so let's say if we skip the string compare, still the value of R0 goes to R3. But if you look here, the value of R2 is basically one of your string. So even if you try to skip this one, the value will not really work. That's why sometimes you don't just try to skip it. You also try to corrupt the instruction so that you're getting what you want. And there's still more. We can also glitch the compare instruction, for example. Here we are comparing the result with 0. Here also we can corrupt the instruction so the flag is not set, and then your BNE will not execute. And you can also change the BNE to BEQ, which means you're basically flipping the whole if-else condition. So in this case, again, just one bit flip. If you flip just one, then you can just change the whole code flow. So this is just so in this case, we have so many instructions we can glitch. This is basically called as fault modeling. Again, I'm just using one glitch as a model. There are still more models you can use, 2-bit flips, 3-bit flips. The reason why I went for 1-bit flip is there are very low chances for it to control, for example, 2 different glitches. For example, if I want to set the first one to 1 and then this one to 1, it's very hard to glitch it because glitching is sort of, even if you have a controllable glitch, it's very hard to set these 2 random values. But for you to have flip over single one, there are high chances that you can tamper with them. So some of the mitigations people, so I used to work for a certification lab who certifies chip level stuff. So these are some of the mitigations which we use. One is the complex number. From a C perspective, okay, fine. So we have count equal to 0, 1, 1, and then if count, then you do your pass or fail. So there the value is just true or false 1. So it's very easy for anybody to glitch 0 to 1 or 1 to 0. So then you can also use a complex number. In this case, I chose, 5, 5, and AA. So the Hamming distance between them is almost FF. For example, for 5, 5, it's 0, 1, 0, 1. And for AA, it's going to be 1, 0, 1, 0. So they are basically like complementary. And it may seem like, from a coding perspective, it may seem like a good mitigation. But if you look at the instructions, yeah, I got the bypass. You can see at around 1,800 nanosecond, I have those bypasses. Yeah. So if you look at them, it didn't change a lot. So you still have the earlier part where you're moving all your variables, setting up all your variables. You can still glitch. You can still glitch the compare. Only difference is that the 5, 5 is also inside this one. So only new thing is like you can still glitch the BNE. So here the mitigation doesn't really matter because you still have the previous ones. You can still glitch and then you can bypass it. And here also, yeah, this is BNE, and you can also glitch when you're copying it inside. For example, it's a very nice example. If you skip, so for example, even if you skip this one, it's going to take the R2. In this case, R2 is basically this one. So which means the value is also user controllable. So if you, for example, if it's a password, you can actually put the password as these flag values. And then since it's going to take the first byte, it may set the count value to that one. And then you bypass the string compare check. Yeah, this is another one which people use. From a programmatic perspective, it sounds stupid. For example, you can do double checks. So you have the same string compare twice. You might ask, like, why not use if-else condition? Reason why if-else condition is not a good idea is because you will include a lot of branch instructions, which means it just takes one glitch to break out of the branch and then go to your, let's say, past test case in this case. And can I glitch it? Obviously, I can glitch it. You can see there are 2 sections, around 2,000 nanosecond, one is around 3,200 nanosecond. And you can see they are like in parts. In the loop, we saw that the glitch were everywhere. But in this code, you can actually see it's very localized towards a specific time duration. So which means those glitches are from a specific instruction being glitched. That's why we are 2 sections. That's why modeling helps you understand which instruction is actually being glitched. Then you can, maybe if you want to fix it, you can fix it. Or you can go a bit more in depth to understand how it works. And you can just zoom into it and then get more glitches. Here, again, not much changes. Here you have 2, but again, you're missing the point that your last check is the main deciding factor. Even though if you have your first one wrong, you can still glitch your second part, and whatever the model which we identified, it's going to be the same, which means you just need to glitch at the second point. Or for example, if you're planning to glitch the branch instruction, you can also corrupt the branch instruction so that it can jump to a different path. So I think in ARM, you don't just jump with the address, you jump with an offset. So which means even if you glitch to add a few more address, you can basically make your PC or your value to go to a different offset, and then you can pretty much bypass it. Yeah, this is another one. So since we know most of the codes are linear, so which means you know that at a specific nanosecond it's going to be this instruction, at a few nanoseconds it's going to be this instruction. So what if you add a delay in it? This is also something commonly used. I've added a random delay before and after, so which means it's very hard for anybody to, for example, reproduce an attack. This is very commonly used these days, but we can still glitch it. So the idea is that we have two random delays, but your operation is there. It may shift left and right, but your delta may not be there, but in the middle part will still be your main operation. It may be random, but since it's a random, we can also use our randomness to glitch a lot of units, and then based on the luck, maybe, you can attack a specific instruction. So in this case, you can see there's no glitch on the top part, there's no glitch on the bottom side, but only on the middle section around 3 to 5 microsecond, you can see those red. So which means the glitches on the middle part, actually we are able to bypass it. Here it's very hard to model this one because this instruction keeps moving left and right because we have random that is shifting this whole instruction. So it's very hard to reproduce because it's random. So instruction will not be the same, for example, for a specific round. And there is another mitigation people use, that's your state check. This is most prominent in the boot stages. For example, first stage would be to copy the memory from my flash memory, and then copy it into my RAM, and then do my hash check, and then boot from a physical address. So each one will have a state. They also configure a variable which is state 1. If the state 2 is not correct, then reset. If the state 3 is not state 2, then reset. So you basically have another variable with a specific value. Can we bypass this? Yes, technically we can do it with almost 0.98%. It may seem like a very small number, but for me to run this 10,000 attacks, it took me probably half an hour. Because, for example, a really good number would be 10 million. So right now in the certification industry, if you can glitch something in 10 million, which means that's not secure. So only if you go more than 10 million, still it becomes complicated. But for an attacker, 10 million is not a big deal. So for them, for example, a smart card, or let's say your credit card. So for example, for an attacker to take the key from a credit card, they can spend a month, and then they can do it for 100 million or even more, and then they can extract the key. And then once you have the key, then you can pretty much do any transaction. So in this case, it's very hard to model. This is where magic comes into picture. Sometimes you really cannot model a fault because some of the faults could be, sometimes you glitch and then it doesn't really show directly. It'll corrupt something in the chip. In the next run, that fault will be reintroduced. So here it's really hard to decode. So in this case, you can model it, but it's fairly difficult to model them. Yeah, so this is something I personally do. I'm known for doing this. So usually, at least from a certification world also, people don't consider multiple glitch. People usually go for a single glitch. You have your window, you glitch once, and then that's all. But in an earlier case, we saw that we have a random delay, and then it's going to move in a very faster way. So we have to make sure we are increasing our probability of hitting those golden sweet spot. So it's also useful to inject multiple glitch so that you are actually covering more space than your randomness. So for example, the same code I injected two 2 glitches. So now I have like almost double the percentage, 1.49. But if I increase the glitch more, then it becomes 31. That is because if you inject too many glitches, then you're basically making your CPU not work. So most of your attempts will go on your system rebooting or just being corrupted. So it's also important to know what exactly the sweet spot of number of glitches as well. In the past, I have glitched devices with almost like 10 to 15 glitches. Sometimes even single glitch will work. So there's something here to experiment with your specific target. So what did we cover? OK, that was pretty quick. But yeah, so we gave a very introduction into how fault injection works, and also we gave a little bit of understanding of how do you model a fault injection, because people have been trying fault injection to bypass the JTAG interface or to the read-back protection of the flash memory. So they are pretty much hitting randomly. Now you just connect your device, glitch randomly, and then expect something good happen. That may work, but moving forward, it's also important for people to understand how to model a fault, so you know why something is bypassed. And then what are different mitigations people are using or have been using, and then how they are pretty much useless. And then how multi-glitches are useful to some extent. And sometimes some glitches you cannot model them because everything relies on the randomness. Another thing about the fixes is also, so right now all the code were compiled with zero optimization, so which means none of the mitigation are removed. For example, the double check. If you compile it on your target with optimization, your compiler is going to say, I don't care about your double check. I'm just going to remove one of your check. So which means even if you implement a decent mitigation, your compiler is going to remove it. And also it's a bit tricky since you deal with assembly. You fix one instruction or one piece of code in your function. You recompile it, and your code will change because your compiler will implement optimization, change the whole binary, your opcode, and then that's also really hard to fix. What you can do from an application perspective, there's not much you can do because fault injection is fairly new, and it's not really, our application current technology is not really up to the stand for mitigating all these fault injection. So what you can probably do is, for example, on your security-related code, let's say if you're building a hardware device which has a unlocking feature, and you have a password for it, maybe you can put some bit of security there. It's possible to bypass it. So here it's not like a software bypass. Okay, you have buffer overflow, you check your the length, and then you fix it, and your device is secure. But in these fault injection, there's no such thing as fully secure. Here it's just a matter of whether you're attacking it 1,000,000 times or whether you're attacking it like 100 million times. So you can bypass pretty much any hardware level security that are there. Or you can rely on hardware level security. For example, there are some really expensive chips which supports hardware level security. So for example, for the voltage glitch, there are chips which has an internal voltage monitor. It will monitor any glitches, and then it will not boot. And there are some chips which has a light sensor inside. Even if you remove the IC and put a laser, then your device will not boot as well. And they are really expensive chips. So if you're making a commercial device, and then if you're going to invest, let's say, 50 euros on a single chip, that is not really viable. And that's why it becomes really tricky as well. And all these mitigations are also not that bad. It is easy to bypass. Again, just like any security, it's also to make things harder for an attacker. The same 1 million to 100 million. It is fine to implement all these mitigations. But it's still the idea is to make time for the attacker a bit harder. And then do a source code, not just source code review, and also look for the instruction level paths in your security-related codes. And I have put all the codes, the framework. I have put all the codes, all the frameworks that is needed to run all these experiments. I have chosen Arduino as the base to implement all these mitigations and the whole framework around it. Why Arduino is because fault injection so far has been considered like a sophisticated attack, but it not really is. In my opinion, it's way more dumber than a software attack. For example, I find buffer overflow more complicated than fault injection because here you just rely on the electronics part of it. You just hit something, just wait for it to happen, and that's all. That's why I made it on Arduino. So this has multiple applications. You can do your characterization. All these checks are also there. You can find it in this link. And any questions, or did I bore you too much?
I can see already, Arun, we do have first question.
I have a couple of questions. Basically, you are glitching using random intervals. So you are not synchronizing your glitching device to the clock of the device under test. Is it correct?
You don't have to. So you can also synchronize your clock. If you want a very precise, if you glitch only a specific instruction, then you can synchronize this. For example, the chip whisperer tool, it has an ability to supply clock to your target, and also at what clock do you want to glitch. So you can also do that, but you don't need to really do that. Sometimes, so usually, like not all chips are same. So because of the way your chips are fabricated, so your instruction will actually have some sort of a jitter. So you don't necessarily need to have a synchronized one. You can just randomly glitch based upon, let's say, a specific trigger, which you already know, and then you can just glitch as well. It's just a matter of if you have a precise timing, it's easier to glitch. But even if you don't have it, it will take a bit more time, but you can still glitch it. It shouldn't be a big problem.
So I suppose after you glitch, you analyze the response to see if you have glitched the correct instruction. And I suppose then you, for the next trial, you reboot the system under test. So this means that to make many times this kind of test,
yes,
you have to account for the reboot time. So
some of these attacks are not persistent. So which means if you reboot it, it goes back to the original state. For example, if your code flow is something that sets a value in your machine, for example, let's say if you're enabling a feature, and then there's a loop that says, okay, fine, if this feature, if the password is correct, enable a bit in my memory to enable some secret feature. If you glitch there, if you can set that value, then the feature will be persistent, but the glitch is not persistent. So it will only work as long as the glitch worked, and then if you restart it, then your code will work as normal.
And another stupid question, but I don't know the exact technology of the chip. But isn't it possible to put the capacitor inside the chip to limit the effect of the glitch?
Yes, that is one of the mitigation. But the problem with that is like that only mitigates voltage-based glitches. If the voltage doesn't work, then I can go for EMFI. So where then I can use a small coil and then like glitch directly on the CPU. Or you can also use laser. So because laser, you directly hit the photon on the metal layer and then create charges. So they help in mitigating, but they don't really necessarily mitigate completely. So even if you have a, let's say, a capacitor, you can use a powerful glitch. Instead of shorting it to ground, you can also short it to a negative voltage so that you drain the capacitor way faster, and then you can still inject the glitch.
Thank you.
Thank you as well.
When you showed the schematics, you showed that you controlled only one VCC pin for the device.
Yep.
So a few questions about that. A, do you choose a specific one? Why not all of them? And why not glitch the PSU?
1 second. Can you repeat the question? Maybe.
Yeah, so you use a MOSFET to glitch one VCC.
Yep.
Why not glitch all of them, or should you glitch all of them, and why not glitch the power supply?
So in this case, 3.3, 3.3, they are all internally connected. So my this STM doesn't have a different power domain. So they have only one power domain. So glitching on the power supply or glitching on this 3.3 doesn't matter because internally it's all routed through one internal regulator. So in a complicated system, for example, let's say if you have a, let's say your mobile phone. So they have several power domain. There will be a power domain for your ADC, your power domain for your CPU, one for your crypto core, one for your RAM, ROM. So then you need to glitch them individually if you want to attack them. But in this case, a very simple target. So they have only one power domain. So you can just glitch through it.
Okay, thank you.
Thank you.
Do we have any more questions from the floor? Oh, we have one from our remote colleagues.
Hi. So the first remote question is, in what real-life scenarios can these techniques be used for hacking?
So one of the things I recently, or like I think 2 cases I can give you an example. I think 3 or 4 years back, I was able to bypass Android MDM, mobile device management, using just a simple gas lighter. So there, for example, they have locked the bootloader access, so which means I cannot go to the Android bootloader. So I was able to corrupt the RAM so that the device goes to a failsafe. That's basically a recovery. So from there, you can pretty much reflash the device or take all your data from it.
Okay, thank you. Another remote question is, what makes you move towards glitching hardware? It's a more personal question.
Sorry, come again?
So the question is referring to what made you do hardware glitching. What was the turning point or event in your life that?
Because you don't do a lot of work, you just let it run, it'll magically work. So it's not like a software testing where you need to, okay, fine, this is my PC value, I need to fill my buffer, I don't need to think that far. You just make your glitching to scan randomly, and then you have your money for it.
Okay, thank you. There are no more remote questions.
Okay, thank you. Anybody else from the floor? No, in which case, Arun, again, thank you.
Thank you so much.